Hello everyone, I'm NITHYA Shri, roll number 22I353 from 3rd BTech ITG2. This video is for the RECode 3 Coding Challenge organized by the Coding Club of PSG Tech. Now, let's look into the problem statement. Here, we are given an N-ary tree and we have to encode this into a binary tree using the left child and right sibling representation. The structure should be maintained and we need to output the pre-order traversal of the encoded binary tree. Now let's see the difference between the N-ary tree and the binary tree. N-ary trees are the tree data structure that allow us to have up to n children for each of the nodes, differing from the binary tree which allows only up to 2 children nodes for each node. This slide has the algorithm steps. So basically we first build an adjacency list to store the N-ary trees. Then we perform the DFS on the N-ary trees to encode it into a binary tree. DFS is nothing but depth first search. And finally we implement the pre-order traversals for the encoded binary tree and print the results. Let's explore this in detail in the next slide with a sample example. Here, a N-ary tree is given. So the first step is to represent this in an adjacency list. Node 1 has 3 children, 2, 3 and 4. So the entry in the adjacency list is like this. Moving on, the node 2 has children 5 and 6. So the entry is represented like this. Node 3, 4, 5 and 6 has no children. So their entries are represented like this. The first step is completed. Now let's look into the second and third step. Here we have to convert the N-ary tree into a binary tree using specific conversion rules and using the depth first search. A sample N-ary tree is given. Now we take the root as such. Using the conversion rules, the left child in the binary tree corresponds to the first child of the node in the N-ary tree, and the right child in the binary tree corresponds to the next sibling of a node in the N-ary tree. So node 2 becomes the left child of node 1 and the node 3 becomes the right sibling of node 2. The remaining one child node of 1 becomes the right sibling of 3. Moving on to the next node 2, 2 has 2 children 5 and 6. Using the same conversion rule, 5 becomes the left child of node 2 and 6 becomes the right sibling of the node 5. Node 3 and node 4 do not have any children, so they remain as they are. This is the final encoded binary tree. So the step 3 is completed in the previous slide. Let's look into the final step, that is to construct the pre-order traversal. So this is a given binary tree. We have to represent it into a pre-order traversal, that is root, left and right. Here I have a small trick to find out the pre-order traversal. First we have to start with the root node, traverse along the left subtrees including all the children's. Then we go up and then we cover the right subtree and we go up. So this is how we have to write the pre-order traversal. Let's look this in detail. First we write the root node. So 1 is covered here. Next we move down the left subtree. So 2 is returned here. Next we cover 5. So 5 is written here. Next 6 is written here. Since 5 has no left child, we directly move on to the right child and we write 6. Then we traverse up and cover the right subtree. So we write 3. Since 3 has no left child, we cover 4, that is the right child of 3. So this is a final pre-order representation. 1, 2, 5, 6, 3 and 4. So this is what we have obtained here. Now we have completed all 4 steps and we have finally encoded the N-ary tree into a binary tree and represented as a pre-order traversal. Let's dive into the explanation of the code. So here, the class defines the structure of the binary tree node. Int val represents it stores a value of the node. The binary node left points to the left child in the binary tree, which corresponds to the first child in the N-ary tree. Binary tree node right points to the right sibling in the binary tree, which corresponds to the next sibling in the N-ary tree. Static variables. Tree is a map that stores the structure of the N-ary tree. Each node maps to a list of its children. Binary root. This is the root of the encoded binary tree that will be created after encoding the N-ary tree into a binary tree. This is a function encode. This function purpose is to encode the N-ary tree into a binary tree using the left child and right sibling representation, and it recursively converts each node into its children in the N-ary tree into a binary tree structure. First, we have to create a binary node. Here, the binary tree node is created with the current node's value. Next, using the adjacency list, it fetches all the children of the current N-ary node. If the current node has no children, the function returns the binary node as it is. For left child conversion, the first child in the N-ary tree becomes a left child in the binary tree using a recursive call to encode this child. For the right sibling conversion, the remaining children of the N-ary tree becomes the right siblings in the binary tree. This is done by traversing through the rest of the children in the list recursively, encoding each child and assigning it to the right child of the current node. The function preorder. The function performs a preorder traversal of the binary tree and prints the node values. The base case is if the current node is null, the function returns without doing anything. The value of the current node is printed, that is, preorder traversal visits the root first. The function recursively visits left child corresponds to the first child in the N-ary tree and the right child corresponds to the next sibling in the N-ary tree. So this is the main function. Here public is being used as it contains a main function which serves as the entry point of the program. First we take the number of nodes n in the N-ary tree. We take the values of the nodes and store them in an array values, though we don't use the array directly in the encoding. Next we build the adjacency list. For each parent child u, v, we add the child v to the parent's u's list in the adjacency list tree. Next we get the root input, which we read the value of the root node of the N-ary tree. Next encoding is done. The function encode is called to encode the N-ary tree into a binary tree starting from the root. Preorder traversal. After encoding preorder binary root is called to print the preorder traversal of the encoded binary tree. In this slides, all the 5 test cases has been compiled and passed successfully. Moving on, in this slide, I have given a sample custom test case where the number of nodes is 7 and the values of the nodes are 1, 2, 3, 4, 5, 6 and 7. Here the parent-child pair has been given. So the output is 1, 2, 4, 3, 6 and 7. It's been compiled and been passed successfully. Now let's analyze the time and space complexity. The time complexity for constructing the adjacency list takes O of n because we iterate through n-1 edge to construct the adjacency list. So for encoding the N-ary tree into a binary tree, The DFS is called once for each node in the N-ary tree. Since each node is processed once and we recursively traverse its children and siblings, the time complexity is O of n. Pre-order traversal. The pre-order traversal also visits each node exactly once, resulting in O of n time complexity. Space complexity. For the adjacency list, the adjacency list for storing the N-ary tree takes O of n space. Call stack for recursion. The depth of the recursion in worst case could be O of n. In case of a skewed tree where all the nodes are either left or right. Binary tree nodes. We allocate a binary tree node for each N-ary tree. So the space required for the binary tree is O of n. So the overall time complexity and overall space complexity is both O of n, where n is the number of nodes in the N-ary tree. In conclusion, we have successfully encoded the N-ary tree into a binary tree while maintaining its structure and demonstrating that a solution works through multiple test cases. Thank you all for your attention.